Hi all, this is a mini episode in a format I'm hoping to try and get out a little bit more often to keep you updated on the news and latest developments that relate to previous episodes we've done, because every so often I get fascinated by a couple of science and technology stories that make the rounds on social media and in the circles in which we talk, and I want to tell you about them and provide a perspective about what's going on and how it relates to things that we've covered previously, and hopefully even spark a discussion about the stories with you. So if I carry on with this, it's going to be more informal and shorter than a standard show, and, as with all podcasting experiments, highly irregular, but you should be used to that by now. So the story I wanted to discuss at the moment is a new climate science paper that's got an awful lot of media attention over the last few weeks, partly because it fits into this cultural zeitgeist in Europe and North America, where we've just had quite hot summers and heat waves, and we've dealt with forest fires and all kinds of things like that. Incidentally, those of you who follow me on Twitter at PhysicsPod will know that I got kind of annoyed about the coverage of this wave of heat waves, especially in the UK. For the first few days, at least, there were endless comparisons here in the UK to the UK heatwave of 1976. But if you look at a temperature map, you'll see that the two events are really nothing alike. The UK heatwave of 1976 was more or less isolated over the UK and a little bit of Western Europe. This heatwave, the 2018 heatwave, covered practically the entire surface of the globe. The problem, of course, is that the link between extreme weather events like this heatwave and climate change as a whole can be very difficult to explain. We like to think of things in terms of cause and effect, whereas particularly with extreme weather events, we should think about them in terms of probability distributions. Let's start very basic with the weather and climate. Weather is essentially the day-to-day or week-to-week conditions of temperature, precipitation, and so on that we experience. And climate is the average of weather over many, many seasons. So the climate of the UK is generally very different to the climate of Brazil, even though you could probably pick a handful of days out of the year where the weather might be surprisingly similar. And the same is even true, of course, between places like Britain and Italy that aren't that far separated. But the climate of a particular region obviously determines the kinds of weather that you're likely to see on any given day. Here in the UK, a summer's day that reaches 33 degrees Celsius is pretty rare. In Florida, which has a different climate, that kind of temperature, that kind of weather, is far more likely to occur. One way to think about it, especially in terms of these extreme weather events, is a bell curve. If you plotted the temperatures for, let's say, all days in July across the UK over many years, you would find that it formed a bell curve with the average at, say, 20 degrees Celsius. Maybe the bell curve stretches out for 9 degrees Celsius either side, such that getting an 11 degrees Celsius day in July or a 29 degrees Celsius day in July are both uncommon but possible. Climate change shifts the average of that bell curve, and this is something that we can actually see in the observational record. You can see from NASA's own temperature records that over land in the Northern Hemisphere, since the 1960s, that bell curve has shifted to the right by about 1 degree Celsius. In other words, the average of that bell curve, the average July day, for example, would be 21 degrees Celsius in the UK. And over the Northern Hemisphere in general, it shifted on average by that 1 degree Celsius. But when your average shifts, the extremes shift further. In fact, according to the same NASA GISS temperature records, they've shifted by 2 degrees Celsius. So climate change over the last 50 years has meant that uncommon but possible warm summer days in our example have shifted from 29 degrees Celsius to 31 degrees Celsius. So the impact of climate change over the last 50 years has had twice the effect on these extreme events than it's had on the average. The problem is, of course, that for most weather events, you can never definitively say that climate change caused that event to happen. Even in a world without climate change, it might still be possible to get a freak event where we see the exact same global heatwaves, just by coincidence. And if you wait long enough, it probably will happen. Scientists who I work with who study extreme weather event attribution would never look at this heatwave and say, is this caused by climate change? Because it's the wrong question. For most weather events, you can't get a simple yes-no answer. Instead, the approach that they try to take is to run many hundreds of simulations on climate models that are then rescaled by actual historical temperature data. In other words, they'll run 10,000 simulations of the world without human influences and 10,000 with human influences. If you see 500 extreme weather events in the world with climate change and only 100 in the world without climate change, then you'll be able to make a quantitative statement like, climate change made this extreme weather event 5 times more likely, or events like this will now occur once every 10 years rather than once a century. That's not the same as causation. You can never definitively say that it was caused, because you can't rule out the possibility that what you've seen is just a 1 in a 50,000 chance of happening. But of course eventually it becomes as near to caused as makes no odds. If I drink 30 triple vodkas and then go out for a drive and I get in a car accident, imagine I then stand up and argue in court that the accident wasn't really caused by my decision to get drunk, because there's a non-zero probability that I would have gotten into an accident anyway. If you try that argument in court, you will probably be laughed out of the room. Beyond a certain threshold of loading the dice, we're happy to call the game fixed. If you can define that threshold, then, you can eventually start to say, this weather event was so ridiculously unlikely without human influence that it may as well have been caused by climate change. But there is of course a serious tightrope balance for everyone who's concerned with climate change to walk here. Because the most devastating effects of climate change will probably be the increase in probability and extremity of severe weather events. That's what's coming first. Every degree Celsius that we heat up the oceans will, of course, result in sea level rise. The sea level rise takes place over decades, centuries. It's these severe weather events and any potential for them to increase in intensity and severity that will provide the most short-term problems that people will need to be concerned about from climate change. Climate scientists also know, of course, that the further we get away from our standard pre-industrial temperatures, the more and more likely it is that dangerous feedbacks will accelerate the climate system away from our own control. So whenever we do, in fact, see one of these extreme weather events, whenever a severe weather event like the heatwave we've just had happens, we naturally want to draw attention to the fact that we need to do more to adapt and to mitigate climate change, because the science tells us that these events are getting more and more frequent, and if we do nothing and don't address climate change, worse things will lie in store. After all, by the time you've got to the stage where this kind of heatwave happens every year or every 5 years, it's almost already too late to do that much about it. You have to adapt to it then. But we have to be extremely careful not to say this was caused by climate change, because people tend to hear that as, well, now we're in a changed climate, so this will happen every year. And enough people are either baffled by the difference between weather and climate, or else pretend to be, that reinforcing this by accident is a bad idea. Nevertheless, I was mad with the early news coverage of the heatwaves and the wildfires in Europe, North America and Japan. At one point, the BBC News front page, and for listeners abroad, the BBC is constantly accused here of having a liberal political bias. It had 4 or 5 extreme weather-related stories about heatwaves or wildfires, and not one even mentioned climate change anywhere in the article or anywhere in the headline. I think all such articles should feature somewhere in the main body, even if it's not the headline, that many scientific studies have shown that extreme temperature events are made much more likely by anthropogenic climate change. That's a perfectly scientific thing to say. It's backed up by all the evidence. And in fact, it's obvious that if you increase the global average temperature, then the extreme temperature events will become more likely, in the same way that if you add a 1 to every number on your dice, you'll be more likely to roll greater than a 3 and escape the dragon in your D&D game. It is in no way alarmist or overstating the case to say that extreme weather events are made more likely by climate change. It's just providing context to the story. And it's really important context too. Eventually, the BBC and other outlets did step up their game and start to mention the impact of climate change on extreme weather. Although frankly, some of them then went too far again. Whenever you see a scientific story in the news, particularly in the tabloid press, just remember that their key goal is to garner clicks and sell papers. Informing you accurately comes second, and for many outlets, sadly, it's a very distant second. I'm reminded of a paper from years ago that some of my colleagues were involved with. It explained that the most likely temperature increase from doubling carbon dioxide was around 3 degrees Celsius, but that you couldn't rule out values below 1.5 or as high as 11. This was way back in the early 2000s that this paper came out. We've now actually narrowed it somewhat to between 1.5 and 4.5, according to the IPCC. If you actually read that paper, it was clear that 11 Celsius was extremely unlikely, just barely within the realms of physical possibility. It was the most extreme result that couldn't be ruled out. Yet, of course, this was the number that got splashed all over the front pages of tabloids as if that had been the main prediction. And then, of course, years later, people say, you said it was going to get warmer by 11 degrees Celsius, and it never did. Well, no one made that claim, ever. So it's in this context of trying to frame climate-related news stories in as accurate a way as possible, in a world that's more focused on clickbait than accuracy. And we still have to convey the gravity of the situation and the need to take action. In this frame of mind, I'd like to talk about the other big climate-related story that came out recently, which was the Hothouse Earth. So you might have seen lots of news articles on this subject. Here's the BBC's take. Quote, researchers believe we could soon cross a threshold leading to boiling hot temperatures and towering seas in the centuries to come. Even if countries succeed in meeting their CO2 targets, we could still lurch onto this irreversible pathway. Their study shows it could happen if global temperatures rise by 2 Celsius. According to the research paper, crossing into a Hothouse Earth period would see a higher global temperature than at any point during the last 1.2 million years. The climate might stabilise with 4 to 5 degrees Celsius of warming above the pre-industrial age. Thanks to the melting of ice sheets, the seas could be 10 to 60 metres higher than they are now. Essentially, this would mean that some parts of the Earth would become uninhabitable. The impacts would be massive, sometimes abrupt, and undoubtedly disruptive, say the authors. The only upside, if you can call it that, is that the worst impacts may not be felt for a century or two. The downside is that we wouldn't really be able to do anything about it once it starts. End quote. So that was the BBC's take on the Hothouse Earth story, and I'm sure you can find various other takes in your own local or favourite news source. It all arises from a paper from Stefan et al., which is open access. Anyone can read it. It's called Trajectories of the Earth System in the Anthropocene. And it's actually a pretty easy read. There's not too much mathematics in there. There's not too much in there that can't be sort of looked up and read and understood. So by all means, go and read Trajectories of the Earth System in the Anthropocene and see what you think of it yourself. But there are a couple of things to point out here right off the bat. First of all, this is a research perspective. Essentially, it is a literature review. It doesn't contain any particularly new science. It's not some new study with a new and improved climate model, or some additional smoking gun piece of data that demonstrates that the Earth is tipping into this hothouse regime. It is a perspective, one endorsed by a lot of scientists who are way smarter than me, who've synthesized and read lots of different information. But nevertheless, it's a perspective with a degree of speculative opinion. It draws together lots of other scientific papers, and it's not necessarily a new study that is introducing a brand new idea that no one's come up with before. So think of it as an overview of the science that we have, with a salt shaker of opinion added in. That's why saying things like, this study shows, is a little misleading. The study suggests that given the evidence that we have at the moment, this may be a possibility, but it's more speculative than definitively proving anything. So let's talk about the evidence, let's talk about what Stefan et al. Are looking at. The idea here is all based around climate feedbacks. In our episodes on climate change, we discussed this already. The basic idea is that climate is driven by all kinds of things, solar activity, volcanoes, and now, principally, human activities like emitting aerosols and greenhouse gases, that kind of thing. Yet it is also a complex system with many moving parts that can influence itself. Feedbacks occur when changing the climate causes other changes that reinforce or act in the opposite direction to the initial forcing. So, for example, emitting carbon dioxide traps infrared radiation. That heats up the Earth, including the Arctic Circle. That's the direct forcing. But heating the Arctic also causes its sea ice to melt. Sea ice naturally reflects some of the more solar radiation back to space. It's more reflective than the open ocean, so when it's replaced by open ocean, it means that more of the solar radiation is absorbed by the darker ocean. And in turn, this means that that region of the Earth heats up more. And this is one of the reasons why the Arctic Circle heats faster than anywhere else on the globe under climate change. The warming due to this secondary effect, melting ice which reflects less sunlight which heats the Arctic more, is a feedback called the ice albedo feedback. And you can imagine that for every 1 unit of carbon dioxide you put into the atmosphere, you might get slightly more heating due to this effect of melting ice. We've already discussed in these old episodes too an example, in fact, of a pretty stable climate equilibrium that arises precisely due to this feedback. It's called the Snowball Earth. This has happened several times in Earth's distant history. Something, maybe a supervolcano, caused a sudden rapid cooling. Ice sheets expanded from the poles and they in turn reflected more sunlight, which caused the Earth to cool further. Eventually the Earth can be entirely covered with ice or slush under this scenario, until you get another big kick. For example, from bacteria that increase carbon dioxide levels in the atmosphere to reverse the trajectory again. So you can imagine the Earth system as moving around and finding these stable points and then being kicked away and moving on another trajectory that takes it towards another stable point. Kind of like a dynamical system in mathematics. That's the analogy that people are looking at. So we know from Earth's history that it's perfectly feasible that you can kick the climate system into a position where these feedbacks take over and in fact become the dominant effect. At this point, although your direct forcing is still important, the climate feedbacks that result can push you the rest of the way. So it might be that cooling the whole planet by a few degrees Celsius would be enough to trigger a snowball Earth, which would then run away with itself and result in far more cooling than the initial kick that you gave it. What the scientists of the Hothouse Earth paper are proposing is that there might be another fairly stable point that feedbacks can lead us to, another state of the climate that's relatively robust like the Snowball Earth. But instead it's 4 to 5 degrees Celsius warmer than the world we live in today. And you can imagine, for example, that a world without ice caps is also, in a sense, a point of inflection on the Earth's possible trajectory. Because there, the ice albedo feedback stops, and so, in some sense, some of the things that are causing the Earth to continue to heat slow down. Their argument is that perhaps a warming of 2 Celsius, in other words, where we'll likely be at mid-century without any major action, might be enough to trigger one feedback, which then triggers another, in a disastrous domino-style effect that kicks the climate on this new trajectory towards this new, warmer, hothouse Earth. And the point is very important to make. I'm not rubbishing this idea. What I'm concerned about is how accurately we express this idea. What I'm concerned about is the sense of certainty that might come with reading this paper, whereas in reality, it's not as certain as all that. Let's talk about some of the feedbacks they mentioned. One we've already discussed, ice albedo feedbacks. The Arctic summer sea ice is smaller than it's ever been on record. This is leading to the heating of the Arctic Circle. As the summer sea ice shrinks and that area of the Earth heats up, it might destabilise the ice sheet over Greenland, which in turn would heat the planet more, resulting in a tipping point for the Antarctic ice sheet, which is currently pretty stable for a variety of different reasons, give or take a few major glaciers, which would then in turn start to melt. So you can see the domino effect of the Arctic sea ice falling into the Greenland sheet, falling into the Antarctic sheet, and gradually the feedbacks accelerate and run away with themselves, and the human influence becomes less important. Another class of feedbacks that were considered are carbon cycle feedbacks. Currently, more than half of the CO2 that we emit is absorbed by the land, plants mainly, or the oceans. It makes some of the plants grow quicker, and it makes the oceans more acidic, but it doesn't go into the atmosphere and impact the climate. But as the world warms, there's a risk that forests, such as the Amazon rainforest or the boreal forests in high northern latitudes, would start to die, and may even become a net source rather than a net sink of carbon dioxide. In other words, not only might the land and ocean become less effective sponges mopping up our CO2, but they might actively start emitting extra CO2 to the atmosphere on top of what humans already do, which can only make things worse. Similar concerns arise due to respiration rates of bacteria in the ocean. In a more acidic and warmer ocean, these bacteria might respire more and emit more carbon dioxide to the atmosphere. The circulation of the oceans is driven by temperature and by salinity, or by salt concentrations. In a warmer world, you might have fresh water from Greenland or glaciers diluting the ocean, and that circulation can change. Water has a much greater heat capacity than air. This will be clear to anyone who's left a bowl of hot water lying around. Maybe you did the washing or something and you left it out. You'll notice that it stays warm for much, much longer than the air around it will. This means that the oceans thus far have taken up around 95% of the additional thermal energy that's kicking around in the climate system due to human influences. In other words, the extra heat that we've trapped on Earth, 95% of it has been absorbed by the oceans. But you can imagine that in the future, if the ocean circulation changes, the oceans could become less effective at taking up heat. Perhaps they circulate this heat energy down to the deeps more slowly. And if that happens, then more heat may end up heating the atmosphere. And on the more exotic side of things, something that people like to worry about a lot, there is permafrost, permanently frozen ground. This is up in the Arctic Circle, and due to dead organisms and things in there, it contains an awful lot of methane, which is a potent greenhouse gas. If that permafrost thaws, as it's starting to, the methane could be released, which would lead to rapid and sudden warming. A few years ago, and today amongst a group of deeply concerned people, it was the green apocalypse. Recent studies suggest that it might be more of a slow burn that takes decades or centuries to fully arrive, rather than a sudden cataclysm. You'll notice a lot of the following in these previous descriptions: may, might, could. The reality is that to fully understand all of these climate feedbacks requires a huge amount of science and a great deal of expertise in fields as diverse as the study of peat soils, the biogeochemistry of the oceans, and how bacteria respire. But what's more, and I think the real reason for the concern around 2 degrees Celsius, is that we're talking about conditions that the Earth has never seen before, at least not in any records that we have of it. When we cross the 2 degrees Celsius Paris threshold, it will take us out of the range of temperatures during which human civilization has ever existed, into a world we haven't seen for hundreds of thousands of years. The whole range of temperatures for the last geological epoch has been around plus or minus 1 degree Celsius. We're already, this decade, moving out of what the world has known of late. So what do we really have here? We have plenty of very real feedback mechanisms that might kick the planet onto a new trajectory. But it's very difficult to quantify how bad they might be, or when they'd kick in. And we also know that in the past, paleoclimate records have shown rapid warming events that did happen, that resulted in Earth being 4 to 5 degrees Celsius warmer than it is today. Much of that may have been due to feedbacks, but the climate is in a totally different state today. The feedbacks themselves could operate differently. We do not have very many reliable data points for how the Earth will respond to something that's never happened before. And unlike in other branches of science, we don't have miniature Earths to do experiments on. We just have our models, and the models aren't as fantastic as modelling feedbacks as we'd like. This is where we get to the framing question, and why I really wanted to talk about this particular paper. For all sorts of reasons, many of them political, I can understand why the authors and journalists want to point out that there are these feedbacks that aren't being taken into account properly in scientific models, that aren't being taken into account properly in people's thinking. People think, oh, if we manage to limit warming to 3 degrees Celsius, that's all we'll get. But they don't know that for sure. Maybe by the time we warm to 3 degrees Celsius, we trigger this cascade of feedbacks and we end up uncontrollably warming to much more than that. So without taking these feedbacks into account, our estimates for how bad things are going to be underestimates. So you can understand why the author and the journalist want to point this out, and why they want to say, if we fail to hold to the Paris limit on temperatures, then all of these feedbacks will kick in and the world could warm by 4 or 5 degrees Celsius. But the problem is then when you phrase it as, and there'll be no stopping it. They may well be right. The 2 degrees Celsius Paris limit is important because it represents uncharted waters for a climate setup like the one we have today. Here be dragons, and here, maybe, be accelerating feedbacks. It would be madness not to warn people, especially when we've spent 30 years warning people, during which time carbon emissions have risen pretty much every year, save for the Great Recession. In some ways, though, this paper, rather than necessarily giving new information, reminds us of all of the risks we still can't be sure about. What concerns me is drawing thresholds in climate science. I appreciate that a domino effect could be possible. We know that some feedbacks, like forest diebacks and Arctic sea ice, are going to be triggered before others, like the permafrost, Greenland, and the Antarctic ice cap. So it makes sense to say that perhaps getting to 2C triggers some feedbacks at 2C that pushes to 3C, where more feedbacks will push us in turn further away. But we cannot allow this to be phrased as, if we miss the Paris Agreement, it's all over, because we simply don't know that that's the case. This paper in no way conclusively proves that. It just points out that feedbacks exist, and that they aren't represented very well in our climate models, and that they could cascade over timescales of decades or centuries if we don't take action. It doesn't show that, as is sometimes being reported or implied, after 2C it's all over and you might as well burn all the oil you want. And this is the problem. This is an area that I think we're getting into in the discourse over climate science, and I understand because people are frustrated after so many years of saying things and not talking about it, but it's this area of defeatism. Defeatism is a form of denialism. Saying, oh, it's too late, we're already doomed, we have no hope whatsoever, we might as well just, enjoy our lives while we still can. This is just another way of not dealing with the problem. And the problem, from some perspectives, is not actually that difficult to deal with. After all, isn't it just a very wealthy industry that has a problem with disposing its waste? A very, very wealthy industry, the energy industry, that can't dispose of its waste in carbon dioxide. The issue, of course, with this defeatism is that 2 degrees Celsius isn't the end, not if you keep going. It gets worse and worse and worse. So the obvious thing to do is to act in as bold a way as you can, as fast as you can, in as effective a way as you can to cut down carbon emissions to avoid these risks that will show up in the future. You see, what seems most likely is that all of these feedbacks will just get worse and worse and worse the further from our nice, stable, Holocene climate that we drift. It's not like you're suddenly flipping switches of feedbacks that turn them on and off. Rather, the more carbon dioxide we emit, the more feedbacks will trigger, and the worse the outcome is likely to be. And then there's more risks for humans as well. A 4 degrees Celsius world has more risks of feedbacks and more risks to humans than a 3 degrees Celsius world, which has more risks than a 2 degrees Celsius world, and so on. Targets and goals give us something to aim for, something concrete to agree upon and build realistic plans around, but our ultimate goal should always be to reduce our dependence on fossil fuels, and more broadly, reduce our dependence on a way of life that does inevitable and irreversible damage to the environment as quickly as we possibly can. We're driving, a little drunk, at top speed, in the fog. No one knows how near the cliffs might be, but that's hardly a good reason to speed up. So this was the rather lengthy minisode on the recent heatwaves and the Hothouse Earth. I urge you to read up on the Stefan et al. Paper and see how your favourite news outlets have covered it. As we learn more about feedbacks in the years to come, we'll hopefully get a greater understanding of how likely a Hothouse Earth is to happen in reality, and whether we can see any signs that these feedbacks are taking effect. But the risk is always worth bearing in mind. When you move into unprecedented territory, there's a real danger that things will spiral out of our control altogether. The faster we act and the more cautiously we behave, the less likely that is to happen. I'll see you next time.